Hello, my name is Emma Hayden, and welcome to my Physics 2211 Lab 5 presentation on the motion of a falling slinky. In this lab, I used both tracker and glow script to analyze and model how a slinky behaves when it's dropped, and more importantly, why the bottom of the slinky seems to stay suspended in midair before collapsing. The main goal of my lab was to predict how a slinky falls and understand how its surroundings affect its motion. I first used tracker to analyze the slinky's actual motion from a vertiseum video, and then I used GlowScript to build a computational model that shows the ideal behavior. My main question was whether the bottom of the slinky would stay still while the top collapses, and when I compared the model to the data, I found that, other than small fluctuations, the bottom really does remain almost perfectly stationary during the fall. To model the slinky accurately, I used three main physics principles. First is Newton's second law, which tells us how the momentum changes when there's a net force acting on an object. This gives us the velocity and position update equations we use in GlowScript. Second is drag force. Since the slinky is moving through the air, there's a small amount of air resistance opposing the motion. In the model, this drag is proportional to the square of the velocity. And finally, we have gravity and the slinky tension. Gravity pulls downward and the slinky provides an upward tension force. When the bottom stays still, that means these two forces perfectly balance each other out, giving a net force of 0. In Tracker, I started by recording the motion of the bottom of the slinky. The mass used was 0.218 kilograms and the drop height was 1.75 meters. I also extracted the initial position from the tracker data and set the initial velocity to 0 since the slinky starts from rest. These measurements were essential because they determine how accurate the computational model is when I compare it to real-world motion. Next, I set up these initial conditions in GlowScript. This included assigning the mass, the initial position, the starting velocity, and the drag constant. The drag constant, in particular, required some trial and error to match the tracker data closely. This helps the model adjust for the slight air resistance acting on the slinky. In the first phase, the bottom of the slinky doesn't move. Since it's stationary, the net force must be 0. Gravity pulls down, and the tension from the slinky pulls up with the same magnitude. Because of this balance, the position of the bottom stays constant during this time. The computational runs in two phases. Then, once the top of the slinky collapses down and reaches the bottom, the slinky begins to fall as a whole. At that point, the net force is no longer 0. Now both gravity and drag act together, causing the slinky to accelerate downward. The velocity and position update equations track these motions frame by frame. So for the results, this graph compares the observed motion to the predicted motion of the bottom of the slinky. As you can see, the computational model matches the real-world data extremely well. Both show that the bottom stays in almost the exact same location until the slinky fully collapses. The small fluctuations in the observed data are likely caused by external forces that the model doesn't include, like slight wind or air currents. There's also some human error. Tracker point placement isn't always perfect. So why does the bottom stay still at all? It's because the forces in the vertical direction cancel out. Gravity pulls downward with a force of mass times the g constant, and the slinky provides an upward tension force of the same magnitude. Since these forces are balanced, the bottom doesn't accelerate. And if we were to attach a heavier weight at the bottom, would it still stay stationary? It depends. As long as the slinky is long enough or has a large enough spring constant so that the tension can match the weight, the bottom would still remain still, at least until the collapsing part of the slinky reaches it. To summarize, my results show that the bottom of the slinky stays nearly stationary throughout the fall. Both the computational model and the tracker data confirm that the upward tension balances the downward gravitational force, keeping the bottom suspended. Any small differences between the model and the real data largely come from air resistance or tracking uncertainty, but overall, the model does an excellent job predicting the slinky's behavior. Thank you for watching.